Now the next thing, we have to study what is the interference of light. So first we have to see what is the principle of superposition. So principle of superposition means obviously you have to find the resultant amplitude. Yeah, so you have to find the resultant amplitude or the resultant intensity of the two waves. So for that you have to consider the effect of each wave separately and then you have to add it. So that what we are going to call it as a principle of superposition. The first wave, second wave, the resultant wave that I have shown over here, so which is having a greater amplitude. So because if I just add their effect, so both of them are in the same phase, so you can find that the intensity has got increased or the amplitude has got increased. So this is what we can say about the principle of superposition for this case. So when I'm just taking the individual effect of each wave and then we just add the effect of all of them. Yeah, so similarly like this, so we can just say about this principle of superposition. So now what is this interference of light? Yeah, so in interference of light, so definitely there is a source of light, so that we will consider. So just we will take the idea for this. So if I just consider that, so this is, let's say, the source of light which I have shown. Obviously this is going to emit the light. Then there are two slits, so there are two apertures. The light is going to pass through them and it will get bent in this manner, something in this manner. Yeah, okay. And again what will happen, the light, because of your second aperture, so similarly you can just consider that for your second case also. Yeah, so for the second case also you can just show it. Yeah, so for the second case likewise, this is how I have just shown for the second case also. Fine. So this is, let's say, S1 and S2. So there is a overlapping and you will say that there is a distribution of intensity will occur. Yeah, so the distribution of intensity will occur and then you will get the different colors. Then you will get the different colors over here. Yeah, and that is what we can say about the intensity distribution. Yeah, so the intensity get distributed and you will get that dark and bright band. You will get, yeah, so the dark and bright band. So likewise, yeah, so the same thing over here you can say that. So this is how there is a interfere. They're going to interfere. Yeah, so at some point there might be constructive interference. They might be in the same phase, or at some point they are out of phase. So when they are out of phase, it will produce the minimum intensity, and when they are in the same phase, they are going to produce the maximum intensity. Yeah, so see, this is the experiment. So that is, we are going to call it as a YDSC. In that there is a monochromatic source of light which you have to consider. The two sources of light should be coherent. That means it is going to produce the waves of same frequency, or there is a constant phase difference between these two waves. Yeah, so this is the most important condition. The width should be very less. They should be close, very close to each other. Then and then only you can observe that pattern carefully, and on the screen which you have to place at a certain distance. Yeah, so you will get the alternate dark and bright band over there. Yeah, so that was nothing but your YDSC experiment. So that we have to just do in just detail also. Yeah, so this is your experiment of your YDSC. So for that, related to that, you have to just find that the various expressions now over here also. So the first expression that we are going to calculate for this case is nothing but the fringe width. Yeah, so this fringe width also you have to calculate. At the same time, we are just going to calculate one more thing, one more important thing. Now that we will calculate, we will just calculate over here about the intensity. Yeah, we will do one, just calculate the intensity for that also. So how to calculate now intensity? So that we will see now. We will see the condition for constructive and destructive interference. So let's say, so obviously just that is a condition for constructive and that is a destructive. Now when the constructive interference will occur, so that we will consider. So for that you have to write down the equation for the individual wave. So let's say y1 is equals to, that is a a1 sine omega t. Similarly, you can write it down y2, that is a a2 sine of omega t plus phi. Then the resultant of that y1 plus y2. Then again I can just write it down. Obviously that is your a1, that is a sine omega t, yeah, plus a2. Okay, similarly you can write it down this sine omega t cos phi plus cos omega t sine phi. Okay, so then this is your a1 sine omega t, a2 sine omega t cos phi plus a2, that is a cos omega t sine phi. So further we can say that obviously. So now what we will do over here, so I can just take that your cos phi also common from this, yeah, fine. So this is your a1, that is a sine omega t, yeah, and again at the same time what you can see that we can take common over here. So for this particular case, so that is a a2 cos phi, yeah, so a2 cos phi, so that is what we can take common, yeah. So this is, I will just write it down one more step over here, or instead of that you can do one thing over here. So you can just take that sine omega t common, and this one, that is a a1 plus a2 cos phi, yeah, and this is again similarly, that is a a2 cos omega t, that is a sine phi. So this a1 plus a2 cos phi is equals to a cos theta, and then this is obviously, then the next thing, that is a a2 sine phi, obviously you can write it down, that is a sine theta, fine. So then this is how we can write it down. So similarly from that, so I will say that, so from these two equations, so let's say obviously this is sine omega t, yeah, and then this is your a cos theta, yeah, and this is again the further that we can write it down, so that is your a sine theta, yeah, and that is a cos omega t. So this is why that a common sine of omega t plus theta. So that is also, you can say that a sine wave, yeah. So definitely after interfering also the resultant wave is also sine wave, yeah. So that is how we can find it out, yeah. So that is what we can do over here. So we can do one more thing that we can do, so that also we can find the condition in which, so you will get that your interference pattern also. So that is also what you can find over here. So this is how we can prove that the resultant wave also is a sine wave. So what we have written over here, that a1 plus a2 cos phi. So let's say this is a1 plus a2 cos phi is nothing but your a cos theta, and again similarly we have just written for your another wave also, that is your a2 sine phi. So this is a2 sine phi is equals to a sine theta. Just taking the square and adding these two equations, so what you will get, that is a a1 plus a2 cos phi square, as well as this is a a2 square sine square phi, yeah, is equals to a square, yeah. So this is a1 square plus 2a1 a2 cos phi plus your a2 square cos square phi, yeah, plus a2 square sine square phi is equals to a square, yeah. So this is a1 square plus a2 square, that is a 2a1 a2 cos phi is equals to a square. So a is equals to obviously square root of a1 square plus a2 square plus 2a1 a2, that is a cos phi, yeah. So or you can also write down in terms of intensity, that intensity, resultant intensity is proportional to the square of amplitude. So this is I1 plus I2 plus 2 into square root of I1 I2, that is a cos phi. Okay, so that is also how you can find the resultant intensity for that case. Yeah, so now, so this is the condition for what we can say the resultant intensity. Either you can find the maximum intensity or also you can find the minimum intensity in that particular case also. So to find the maximum intensity, that is a I max. Yeah, so definitely I can say that. So this is I1 I2 and this is your 2 into square root of I1 I2. Yeah, or also you can say that, so this is nothing but your A1 plus A2 whole square. So that is your I max. And similarly you can find for your I minimum also, that is for phi is equals to 180 degree. Yeah, so that is a A1 minus A2 whole square. So you can just take the ratio of that I max upon I minimum also. So this is A1 plus A2 whole square upon A1 minus A2 whole square. So either you can take any one of that common. So let's say if I just take that A1 common, that is a 1 plus A2 by A1. Yeah, and this is A1 1 minus A2 by A1. Yeah, so this is whole square of that. So this is 1 plus R and that is 1 minus R whole square. So this is also how I can just find that ratio for that I max upon I minimum, and that is how you will get it. Yeah, so in case if I1 is equals to I2 is equals to I, then what is the maximum intensity that you will get? Yeah, so if it is same, then definitely that is a 2I plus again that is a 2I cos phi. Yeah, so for that case, taking that 2I common, 1 plus cos phi. Yeah, so this is again that is a 2I. So 1 plus cos phi is equals to 2 cos square phi by 2, and then that is your 4I cos square phi by 2. So this is what we can say about the maximum intensity. Yeah, so that is also one of the case, so where we can find the maximum intensity for this particular case also. Destructive and constructive interference, that we will see over here. So how exactly we are just going to calculate it. So if let's say these are the two sources S1 and S2 and this is nothing but the screen. So this is how, let's say this is A, B and this is P. Okay, fine. So this is the extra distance that they have to travel. Let's say you can say that, so for example this is a BQ, that is the extra distance which they have to travel. So that is BP, obviously a minus, that is a AP, so that is a path difference. Yeah, so if this path difference and if it is at the center, then obviously both of them has to travel the same distance. Yeah, because it is exactly symmetrical over here. Fine, so this is the path difference. So when we can say that this path difference is multiple of n lambda, so in that case that is the constructive interference that you will get it over here. Yeah, so that is the constructive interference, and the condition for your destructive interference, definitely it is nothing but again we can calculate, that is a 2n minus 1 lambda by 2. Yeah, so that is the condition for your destructive interference. Yeah, so for destructive interference, again this path difference, if it is multiple of your 2n minus 1 lambda by 2, then in that case obviously again that is n is equals to 1 2 3 likewise. So for that case you can say that it is the destructive interference. Yeah, or either you can say that lambda corresponds to a phase shift of 2 pi, then path difference, let's say this is a PD, corresponds to a phase difference of how much? Yeah, so this is 2 pi p upon lambda. Yeah, so that is what we can say that. So obviously which is nothing but the phase shift. Yeah, so this phase shift is corresponds to a 2 pi p upon lambda. Fine, so the same condition that you will get over here for constructive interference, and this one you can say for that is for your destructive interference. So these are the two conditions which are very important for determining the result in case of your YDSC experiment. Yeah, so that is about the constructive. You will get the bright band, and at destructive interference you will get the dark band over there.